Imagine watching a single star explode with more raw energy in 10 seconds than our Sun will release in its entire 10 billion-year lifespan. A cosmic firestorm so intense it can burn brighter than every other star in its galaxy combined. A blast so violent it can forge the heaviest elements in nature, gold, platinum, uranium, then fling them across the universe. These are not the standard supernovas taught in school. These are the universe's rarest, most catastrophic stellar deaths. Hypernovas. A hypernova is the most extreme endpoint of stellar evolution, an event so powerful that its light can outshine everything in the cosmos for a breathless moment. When astronomers detect the faint whisper of a gamma ray burst from billions of light years away, they know they're witnessing the death cry of a star unlike any other. Only the largest, fastest spinning, and most unstable stars ever born can end in such a colossal event. If you love exploring cosmic extremes, monstrous black holes, dying stars, interstellar mysteries, now is the perfect time to subscribe. The universe is full of spectacular phenomena, and hypernovas stand among the most jaw-dropping of them all. Hypernovas begin with stars that are truly colossal. To understand the explosion, you must first understand the lives of these giants. Our Sun is considered small compared to them. Where the Sun has one solar mass, a hypernova progenitor has at least 30. Some reach 90 or more. Stars of this scale burn with impossible intensity. Their cores reach temperatures and pressures that shred atoms apart, fusing them rapidly and violently. These enormous stars form in the densest pockets of galaxies, where the gas is thick and gravity is strong. As a cloud collapses under its own weight, material floods inward, gathering into a blazing core. When fusion ignites, the star lights up with a brightness thousands of times greater than the Sun. But this brilliance comes at a cost. These giants live short and furious lives. Where the Sun may live for billions of years, a hypernova-destined star burns through its nuclear fuel in only a few million. Inside its core, it fuses hydrogen into helium, helium into carbon, carbon into oxygen, oxygen into silicon, and finally, silicon into iron. This chain happens incredibly fast, each stage lasting less time than the one before. Iron is the end of the line. It cannot produce energy through fusion. Once enough iron accumulates, the star's core becomes unstable. The outer layers grow restless as radiation pressure weakens. Gravity begins to win. The star wobbles and swells, its light flickering as if sensing its own fate. Deep inside, the final seconds of its life approach with terrifying speed. A gravitational collapse is imminent. In an ordinary massive star, this collapse leads to a powerful supernova. But in the rarest and most violent cases, those with extreme mass, rapid rotation, or unusually strong magnetic fields, the collapse becomes far more dramatic. These are the stars whose deaths produce hypernovas. Their cores are so massive that when gravity pulls inward, the collapse is total. In an instant, the star's center squeezes into an ultra-dense remnant, either a newborn black hole or a neutron star with a magnetic field so intense that it defies imagination. And that moment is only the beginning. When a hypernova begins, it happens with explosive suddenness. The star's core can no longer support the crushing weight of its own mass. It gives in, collapsing inward at a significant fraction of the speed of light. Protons and electrons are forced together into neutrons. If the core is light enough, it forms a super-dense neutron star. If it is heavier, gravity overwhelms even neutron degeneracy pressure, and a black hole is born. This collapse releases a shockwave of energy. In a typical supernova, this shockwave rebounds outward and blasts the star apart. But inside a hypernova, the situation becomes far more extreme. The star is often spinning too fast for a symmetrical explosion. Its rotation funnels material into a swirling accretion disk around the newborn black hole or magnetar, heating it to unimaginable temperatures. The incredible heat and magnetic chaos inside this disk generate two narrow, focused beams of concentrated energy. These beams burst outward from the star's poles and bore through the collapsing stellar layers. When the beams reach the surface, They erupt into space as deadly blasts of radiation. The jets travel at nearly the speed of light, tearing apart the matter in their path. This jet-driven explosion is the hallmark of a hypernova. Instead of spreading energy evenly in all directions, a hypernova channels a staggering amount of power into these narrow beams. The result is an explosion magnitudes more violent than a supernova, with jets so bright they can be detected across cosmic distances. Meanwhile, the outer layers of the star are shredded and launched outward in an expanding halo of gas and heavy elements. The energy released is enough to reshape entire regions of a galaxy. Gas clouds ignite with new star formation, shockwaves ripple across interstellar space, newly forged heavy elements scatter, later incorporating themselves into planets, moons, and, many billions of years later, living creatures. Everything made of gold, silver, uranium, and platinum owes its existence to events like this. In the vast silence of space, a hypernova is a moment of ultimate violence, tearing apart a star in a cosmic heartbeat and leaving behind a black hole or magnetar as the final remnant of its catastrophic end. One of the most dramatic signatures of a hypernova is the gamma-ray burst, the brightest electromagnetic event known to science. These bursts last only seconds, but in that brief flash, they release more energy than the sun will output over its entire lifetime. When a gamma-ray burst reaches Earth, even after traveling billions of years through space, it arrives as an intense spike on our detectors. A long-duration gamma-ray burst is triggered when the hypernova's twin jets pierce the star's outer layers and blast into open space. As the jets travel, they collide violently with interstellar gas, producing shockwaves that emit gamma rays, the highest energy photons in the universe. These photons race across the cosmos, carrying with them the imprint of the immense explosion that created them. Although they last only seconds, gamma-ray bursts can illuminate galaxies across huge stretches of cosmic time. Some of the most distant bursts ever recorded come from the early universe, from stars that lived and died when galaxies were still forming. Their light carries clues about the conditions of the cosmos as it was billions of years ago. Despite their beauty, gamma-ray bursts represent an existential threat if one ever occurred nearby. A burst aimed directly at Earth could strip away the ozone layer, trigger mass extinctions, and flood the surface with lethal ultraviolet radiation. Fortunately, hypernovas are extremely rare, and the chance of a burst being pointed precisely at Earth is minuscule. Even so, gamma-ray bursts remain one of the most important tools in astronomy. Because they are so bright, they act as cosmic lighthouses, revealing information about the space they pass through. Their afterglows help scientists map distant galaxies, measure interstellar dust, and understand how massive stars die. Every hypernova that occurs leaves behind a trail of information, a brief but powerful signature etched into the fabric of space-time. A hypernova is not only a spectacular death, it is also a profound act of creation. Inside the inferno of the collapsing star, temperatures soar into the billions of degrees. At these unimaginable energies, the matter in the star's core undergoes nuclear reactions that cannot occur under any other conditions in the universe. This is where the periodic table receives its heaviest entries. Elements like gold, platinum, and uranium, the materials that enrich planets and define advanced civilizations, are born from the chaos of this violent explosion. Within the star's final moments, neutrons are produced in overwhelming numbers. These neutrons collide with atomic nuclei, creating heavier isotopes through a process known as rapid neutron capture, or the R process. Each atomic nucleus absorbs neutrons faster than it can decay, climbing up the ladder of atomic mass, forming new and exotic elements in fractions of a second. When the outer layers of the star are blasted into space, these elements scatter throughout the galaxy, seeding the interstellar medium with the raw materials for future worlds. Every planet, moon, organism, and technological device with heavy metals owes its existence to stars that died this way. A hypernova does not merely end a star's life, it ensures that countless new ones can begin. Nebulae rich in heavy elements collapse more easily into stars, forming planetary systems that can sustain complex chemistry. The very gold in human jewelry, the platinum in electronics, and the uranium that powers reactors were forged in the extreme heat of ancient hypernovas. In this sense, a hypernova is a cosmic alchemist, turning the ashes of a dying giant into the ingredients for new cosmic architecture. The explosion is not simply destruction, it is transformation on a scale that defines galaxies. It is the universe renewing itself through fire, ensuring its chemical richness continues to grow with each generation of stars. When the core of a massive star collapses, it produces some of the most extreme objects known to science. In many hypernova events, the collapse creates a black hole, an entity so dense that space-time folds in on itself. A sphere only a few dozen kilometers across can contain more mass than several suns. This newborn black hole becomes the engine of the hypernova, powering the jets and radiation that blast outward into the surrounding galaxy. Yet black holes are only one possible outcome. If the collapsing core does not gather quite enough mass to form a singularity, it becomes a magnetar, a neutron star with a magnetic field trillions of times stronger than Earth's. These magnetic fields are so intense, they can tear apart atoms, distort fundamental particles, and release colossal flares of energy capable of traveling thousands of light years. Both black holes and magnetars represent matter pushed to its absolute limits. A teaspoon of magnetar material would outweigh a mountain on Earth. The gravity of a black hole is so strong that nothing, not even light, can escape once it crosses the event horizon. These remnants are nature's ultimate extremes, preserved snapshots of the hypernova's violent birth. The creation of such an object marks a turning point in the life of a galaxy. The black hole or magnetar remains long after the explosion's light has faded, influencing nearby stars and gas clouds. Over millions of years, these remnants may trigger new waves of star formation, reshape the structure of their stellar neighborhoods, or even merge with other compact objects, producing gravitational waves detectable across the universe. The collapse that births these remnants is the most dramatic phase of a hypernova, but their long-term existence extends the influence of the event far beyond the moment of explosion. They become anchor points of gravitational power, silent and enduring markers of a star that once burned with unimaginable brilliance. Long after a hypernova's initial flash fades, its traces remain imprinted across vast cosmic distances. The shockwave from the explosion expands through interstellar space, sweeping up gas and dust as it travels. Over time, the shockwave forms an enormous bubble, a supernova remnant, filled with turbulent hot plasma and enriched with heavy elements. These remnants can span dozens or even hundreds of light years. As the remnant expands, its influence reshapes the environment around it. Dense clouds of hydrogen may be compressed by the approaching wave of energy, triggering the birth of new stars. This star formation may continue for millions of years, creating bright young clusters populated with hot blue stars. Such regions shine brilliantly in ultraviolet light, proof that death and creation are intertwined throughout the cosmos. Astronomers study these remnants to understand the mechanics of the explosion. By analyzing the distribution of elements, scientists can determine how the hypernova unfolded, how the jets were oriented, and how energy was deposited throughout the star's outer layers. Each remnant becomes a forensic scene, a record of a cosmic catastrophe millions of years in the making. Gamma-ray bursts leave their own subtle footprint. The intense radiation from the burst interacts with interstellar gas, ionizing atoms and creating transient structures that can be detected even billions of light years away. When astronomers search for these signatures, they uncover clues about the early universe, how galaxies formed, how stars evolved, and how cosmic structures changed over time. The legacy of a hypernova can persist for eons. Even when the remnant disperses and fades into the surrounding galaxy, the heavy elements it created remain. They find their way into new planetary systems, into the cores of asteroids, into the atmospheres of developing worlds. The memory of a hypernova lives on in the chemistry of everything that forms afterward. In the rocks beneath our feet and the atoms in our bodies, traces of ancient hypernovas are quietly embedded, reminders that every human being is connected to the violent deaths of stars. A hypernova does not unfold in isolation. When the star explodes, its energy rips outward in every direction, or in the case of a gamma-ray burst, delivers a destructive beam across interstellar space. Any worlds orbiting the doomed star are instantly overwhelmed. Even gas giants are stripped of their atmospheres in seconds, their layers blasted away like mist under a blowtorch. Rocky planets do not fare any better. Their crusts melt, vaporize, or are shattered by shockwaves moving at a fraction of the speed of light. Their moons, atmospheres, oceans, and magnetic fields are all erased in the blink of an eye. But a hypernova's influence reaches far beyond its own system. Light years away, planets orbiting neighboring stars may experience devastating after-effects depending on their distance and the orientation of the jets. A gamma-ray burst striking a planet with an atmosphere can rewrite its chemistry, destroying ozone, triggering mass extinctions, and altering climate cycles for thousands of years. Even worlds protected by strong magnetic fields cannot fully shield themselves, as the sheer volume of radiation overwhelms their defenses. Yet destruction is only half of the story. Over much longer timescales, the heavy elements thrown into space by the explosion drift among the nearby systems. Dust clouds enriched with fresh metals absorb starlight and gather into new protoplanetary disks. Future worlds forming in these regions inherit the chemical wealth of the hypernova. Their cores contain more metals, their atmospheres include complex molecules, and their potential for biological and technological evolution increases dramatically. A hypernova can annihilate an entire planetary system in an instant, but it can also plant the seeds for 1,000 new ones. Its touch is both catastrophic and creative. It sweeps the region clean, then enriches it with the essential ingredients for life. This duality, destruction enabling creation, is one of the most profound themes of cosmic evolution, and nowhere is it more dramatic than in the shadow of a hypernova. Of all cosmic explosions, hypernovas rank among the most luminous. For a brief period, the dying star outshines the combined brilliance of an entire galaxy, containing hundreds of billions of stars. The initial flash is so bright that it burns through the void like a cosmic torch, visible across billions of light years. Light from these blasts can travel for ages before reaching any observer, meaning we witness events that occurred long before our solar system even existed. The radiant output of a hypernova spans the entire electromagnetic spectrum. The first signal is often a surge of gamma rays, the most energetic form of light. This is followed by X-rays, which reveal the hyperheated plasma tearing outward. Then come the ultraviolet and visible wavelengths, illuminating the blast's expanding debris. Finally, as the explosion cools, infrared light emerges, carrying the thermal glow of dust and gas reshaped by the shockwave. For telescopes on Earth and in orbit, a hypernova is a rare cosmic laboratory. Each wavelength carries a different piece of information. Gamma rays reveal the violence of the jets, X-rays trace the shock fronts, visible light maps the ejected material, infrared radiation tells the story of cooling dust that may one day form planets. Astronomers can track these signals for years, watching as the hypernova remnant evolves like a slow-motion film played across the heavens. This light does more than illuminate cosmic history. It challenges our understanding of physics. The energies involved push the boundaries of known science, testing theories of relativity, particle interactions, and magnetism. Every observation of a hypernova becomes a chance to refine the laws governing the universe. The cosmos reveals its secrets through flashes of impossible brightness, gifting humanity fleeting windows into the most extreme phenomena ever observed. When one of these explosions is captured by an observatory, it becomes a landmark event. Each detection adds another chapter to the universe's story, another clue to the origins of elements, galaxies, and cosmic structure. Light from a hypernova is not simply illumination. It is information carried across time, a record written in radiation, waiting patiently for someone to read it. The collapse of a massive star into a black hole or magnetar does not merely release light, it shakes the very fabric of space-time. In the final moments of implosion, when the core squeezes from the size of a planet to the size of a city, gravitational waves ripple outward. These distortions stretch and compress space itself, traveling across the universe at the speed of light. Though subtle by the time they reach Earth, they carry invaluable information about forces and densities impossible to reproduce in any laboratory. A hypernova's gravitational signature is complex and dynamic. The asymmetrical collapse of the core, the rotation of the forming black hole, and the violent turbulence of the surrounding layers all contribute to the pattern of waves radiating outward. Detectors on Earth, with their laser-coated vacuum arms stretching kilometers long, measure changes smaller than the width of an atomic nucleus. Yet these tiny fluctuations reveal the story of a star's final heartbeat. When astronomers decode these signals, they learn how matter behaves under crushing pressures, how black holes spin at birth, how magnetic fields twist and fracture inside neutron stars. Gravitational waves offer a form of observation that bypasses dust, gas, and radiation. They carry pure information, unaffected by the obscuring clouds that hide many stellar explosions from telescopes. Where photons struggle to escape, gravity's ripples flow freely. A hypernova that produces detectable gravitational waves becomes an extraordinary scientific event. It allows physicists to confirm predictions from Einstein's theories and to test ideas about the behavior of matter at nuclear densities. The data provides a rare glimpse into the instant of cosmic transformation, when a star becomes something new and unimaginable. Space-time itself becomes the messenger. Every ripple that reaches Earth is a whisper from across the cosmos, an echo of an event too distant to influence our world directly, but powerful enough to bend the universe's geometry. And in listening to those whispers, humanity gains insight into the deepest structures of reality. In the wake of a hypernova, the universe becomes a forge of elements. During the star's long lifetime, nuclear fusion within its core forged progressively heavier atoms, from hydrogen to helium, carbon, oxygen, silicon, and finally iron. But iron is the gateway, the limit beyond which fusion no longer provides energy. When the core collapses and the hypernova erupts, a sudden and violent rush of neutrons floods the environment. This triggers rapid neutron capture, an extraordinary process known as the R process. Within fractions of a second, elements far heavier than iron, gold, uranium, platinum, thorium, burst into existence. In this brief cosmic moment, an entire periodic table expands. The explosion becomes a cauldron of unimaginable density and temperature, assembling atomic nuclei that would be impossible to create naturally under more peaceful conditions. The sheer abundance of energy and neutrons fuses matter into exotic isotopes that later decay into stable, heavy elements. Each grain of gold on Earth, each speck of platinum in a ring or a computer chip, is a relic of one such ancient blast. The hypernova's debris drifts outward over millennia, mixing with nearby gas clouds. These enriched regions become the birthplaces of new solar systems. Dust grains, metals, and molecules swirl into disks that eventually collapse into stars, planets, comets, and asteroids. The materials that shape terrestrial worlds, and life itself, originate in these moments of destruction. Without hypernovas and their titanic chemistry, the universe would be a sparse place, filled with nothing more than hydrogen, helium, and the faintest traces of lithium. This is one of the paradoxes woven into the fabric of existence. The cosmos requires devastation to evolve. Every explosion contributes to the grand cycle of matter. Every atom in our bodies was once part of a star, and some of those atoms were born not in gentle stellar processes, but in the violent, all-consuming fury of a hypernova. The universe destroys, so that something new can someday take its place. When the hypernova's fury subsides, the star does not simply vanish. What remains becomes one of the strangest objects in the universe, a relic that defies ordinary understanding. The collapsing core may form a black hole, a bottomless well of gravity, where matter is compressed into a point of near infinite density. These newborn black holes often spin at incredible speeds and can pull in the surrounding debris, forming disks of superheated gas that radiate intensely as they whirl close to the event horizon. If the collapsing mass is slightly lower, the result may be a magnetar, a neutron star with a magnetic field trillions of times stronger than Earth's. These magnetic fields warp space and twist plasma into contorted, violent shapes. The surface of a magnetar is solid nuclear matter, and its crust can crack under magnetic stress, producing bursts of gamma rays and X-rays detectable across vast distances. Magnetars are among the most extreme objects known, their fields so powerful they could erase the structure of atoms if one were to pass too close. Surrounding these remnants is the hypernova remnant itself, an expanding bubble of gas and dust that can stretch across dozens of light years. This cloud glows with the afterlight of ionization, sculpted into filaments and knots by the shock waves radiating outward. Over centuries, these remnants evolve into some of the most beautiful and complex nebulae in the cosmos. Their shapes trace the chaotic layers of the explosion, their colors reveal the composition of the ejected elements, and their motion preserves a record of the hypernova's final violent moments. Black holes, magnetars, and nebulae each tell a different story about the death of the star. They are the fossils of cosmic violence, markers of the life cycles that shape galaxies. Their existence shows that even after unimaginable destruction, the universe continues building upon its own ashes. In these remains lies evidence of how stars live and die, and how their endings reshape everything around them. A hypernova is more than a catastrophic event. It is a turning point in the history of the universe. Each explosion sends shockwaves through the interstellar medium, stirring dormant regions of gas that may collapse into new stars. Each generation of stars is richer in heavy elements than the last, slowly transforming the cosmos from a simple sea of hydrogen and helium into a diverse landscape capable of supporting planets, chemistry, and potentially life. The legacy of a hypernova can last billions of years. Planets forged from its remnants may orbit quiet sun-like stars in distant eras. Life might arise on those worlds, building oceans, forests, civilizations, and technologies from elements created in seconds within the original explosion. The gold in a distant civilization's artifacts, the uranium in its reactors, the calcium in its bones, all may trace their origins back to a single colossal detonation. As civilizations look out into the night sky, they may study ancient remnants of long-dead stars, trying to decode the same cosmic fingerprints that astronomers on Earth analyze today. They may ask the same questions we ask now. Where did we come from? What forces shaped us? How did the universe build the raw material of life? And they too would discover that the answers lie not in gentle cosmic processes, but in violent transformations that sculpt the fabric of reality. A hypernova marks the end of one star's life, but it also marks the beginning of thousands more. The universe is vast, ancient, and endlessly creative, and the death of a giant star is one of the most breathtaking expressions of its power. These explosions connect the stars to the galaxies to the elements, and the elements to every living thing that may one day emerge from the dust. In the end, the legacy of a hypernova is not just destruction, it is possibility. It is the promise that even in the universe's most violent moments, something extraordinary is born.